How's it going, everybody? Welcome to DR Electronics, and welcome to my YouTube channel. For my first ever video, I decided it would be best to cover a project that I made in KiCad 5 involving a portable phone charger. Now, this is the first ever project I did from scratch, and to give some context, I've been designing PCBs since May of 2020, and I've been designing ever since. And I've always used KiCad as my main EDA tool. It's free and easy to use. And I feel that a lot of channels that cover electronic engineering and PCB design in general are of people that are already experienced, and they don't exactly go into detail as much as I would like about certain topics that can be rather confusing to newcomers. So that's what I'm intending to do with this channel. But I figured I'd show you where I started off. That way, when I make other videos in the future, it gives some more context. So, as I said before, this project that I made was an attempt to create a portable phone charger, as I felt it would be better off making my own rather than just buying one from eBay or Amazon. I didn't realize at the time how complicated portable phone chargers can be. They are simpler devices compared to other projects that you could do, but for a first project, it was definitely a bit overkill. And you'll definitely see where I struggled and failed with both the schematic and PCB layout. There are a lot of problems with this board. It does not work at all. I did make a newer version a couple years later that does actually charge devices, but that also has its own problems that maybe I could get to in another video in the future. But for now, I just wanted to go over my very first project and talk about the mistakes I've made and what I've learned since. But with that being said, let's jump into the schematic. Looking at our schematic here, we could see that I put each component in its own section. So we'll start off with what I consider the power section, which is the USB Type A connector and 5-volt boost converter. Looking at our USB Type A connector here, it seems that I'm missing ESD protection along with overcurrent protection. So typically what I like to do now for my projects in regards to ESD protection is use an IC that ties to the data plus and data minus lines, which then also ties to the data plus and data minus lines of the microcontroller. And for the fuse, or rather the overcurrent protection, I like to use a fuse in order to protect for those sort of situations in line with VBus. So it's something rather simple, but I didn't have it in the project, either because I didn't know about it or didn't think it was necessary, which either way is still bad practice. Also, this USB Type A connector being in its own section kind of looks strange. I should have just tied it to wherever it was intentionally connected to, which in this case I think is the 5-volt boost converter. With only one part in one section, there's no need to separate it. I understand that I was trying to make things more clear, but it's just unnecessary. Looking at my 5-volt boost converter here, I see that I have a datasheet at the bottom of the box, and this is fine, it's not necessarily wrong, but if I already have the datasheet in the symbol properties itself, it's kind of unnecessary, and it's not something that you see in professional schematics. So this is not something that I try and include now when I create my own schematics. Looking at the boost converter itself, though, I'm noticing how the 5-volt rail is tied to VIN. This is wrong, as it should be the 3.7 lithium-ion battery, because the whole point of a boost converter is to take a voltage and make it higher. So if we have a 3.7 to 4.2 voltage input, it's a given range depending on the amount of charge it has, we expect a 5-volt output, not a 5-volt input with a 5-volt output. That just doesn't make any sense. That would basically just be like an op-amp buffer, but we're not using op-amps for this. We're trying to use boost converter circuitry. So another issue that I notice here is the feedback pin is being pulled to ground, and it's not even the same ground that I used on my USB Type A connector. It's ground reference, and I also have ground power. Again, not really sure why I was doing that. I think I did because on the actual datasheet of the part itself, it shows multiple ground references, which just isn't necessary. For a project like this, you want ground to be the same for all components. It's strictly DC and low voltage, so there's really no need for it. Also, with this particular boost converter that I chose, it is one of those where you can make it either adjustable or fixed. Now, the fixed version of the boost converter needs the feedback pin directly tied to Vout without its feedback resistors. However, I just tied my feedback pin to ground. So essentially, that pin is getting shorted, which means that this boost converter could never actually boost voltage, and if anything, it can't even output voltage. So not only does it not boost, but it doesn't output voltage. So it has two problems in one. And in terms of boost converter calculations, like knowing what to use and where to find the formulas, what I would recommend is Texas Instruments application note regarding this. So they go over how to choose feedback resistors, duty cycles, switching current, inductor selection, input and output capacitor selection. Everything that you would pretty much need in order to make a fairly basic boost converter would be in this application note. And I'll provide a link for it in the description below. So yeah, this boost converter circuitry is entirely wrong. It doesn't do anything right now. And another issue that I have in regards to the connectors is I don't have a connector to actually charge the lithium-ion battery. So for a charging device, you need one connector to charge the battery, and then you need another connector to charge your load. Right now, I just have the connector that charges your load. So this schematic and this design and layout basically has no way of actually charging the battery that it's powered off of. So it would never work with the way that it's configured. But again, this was my first project, so there was bound to be a lot of mistakes and just a lot of inconsistencies because there's just a lot of fundamental concepts at the time that I just really did not understand. But with that being said, we'll now move on to the protection circuitry section and the charging section. Looking at our battery protection IC, it seems to have the same issues that the other two sections had. So once again, the datasheet link is present, which is just not needed as I put it in the symbol properties, although the datasheet that I put here, the link is no longer valid, so I should have updated that at the time. Looking at the actual symbol and pin placement, it's not great as there are wires crossing with each other, and it just seems rather sloppy. What you should do typically is under the datasheet, it'll have a typical application circuit where it will show the symbol and how components should be tied to it. You should follow this. There will be cases where their typical application circuit is not great or they don't even have one at all. If they don't have it, then have your input pins on the left and your output pins on the right to the best of your ability. But I think in the case of this particular IC, I should have just followed it. It would have looked a lot better. Also, some of my text here is being covered by the dotted lines. So the battery plus and battery minus symbol is being covered here, and the actual symbol itself is not great. I should have just created a custom symbol that would have looked better. The P plus global label here is also being covered by it, and labels in general, I try and keep them horizontal. Try and keep them one direction, as vertical labels are a bit harder to read. Same thing goes for these resistors here, where I have the reference designator inside of the resistor. This should be on the outside along with the actual resistor value itself. And I'm noticing here that this is just 330. So I don't know if this is a 330 ohm, kilo ohm, or mega ohm resistor. I know that it's a 330 ohm resistor because I made the project, but someone reading this wouldn't know that. So that's something that I should have put there. And looking at our choices in MOSFETs, I believe that the current is rather low on these, only at 120 milliamps. Now I did choose the right drive voltage, 2.6 volts, but the actual current or maximum current output is pretty low. And that can even be said for the boost converter, which only outputs up to 200 milliamps of current. So this charger would have been really, really slow, which again is not great. And looking at our ground symbol here for the protection IC, this is another problem. So it does show this in the datasheet. However, this is an instance where the datasheet is wrong. You want the ground symbol after the MOSFETs so that if one of these turn on or turn off, depending on the given over current or over voltage condition, it will actually protect the battery. Otherwise, this battery will not be protected, and this entire part of the circuit is useless. So that's something that I probably should have looked into at the time, or at least asked questions about it. It's not something I would have known, but again, with the way that this is configured, this circuit for the battery is doing nothing. So that's pretty much that with regarding the protection section. Regarding the charging section here, right away, if you could see here, The P plus and P minus global label, once again, they're vertical for some reason. They're both tied to VBAT. So I'm essentially shorting the battery. I think at the time I really didn't understand the concept of completing a circuit and tying it back to ground. I was very confused with how that worked in regards to making your own schematics and tying different components together. So I think I was trying to complete the circuit in my mind, and this is the way I did it. Also, in terms of the rest of the circuit, again, more of the same issues. This is missing its full designation. R7 should not be inside the resistor. This is also just off-centered. Same with this cap value. It's away from C6, which is also rather strange. The actual charging IC itself is fine. I pretty much just copied and pasted the typical application. For this particular IC, I have used it in other projects. You can get away with that, but in general, I don't recommend that. Read the data sheet, know what calculations you need to perform, and make sure you chose the right parts and values for them and right package size. Because I believe for some of these capacitors, I chose an 0603 footprint, but then I purchased an 0805 part. Again, at the time, I didn't understand the difference between the actual sizes for surface mount components, because this entire board was intended to be surface mount other than the USB type A connector. So that's another thing that's really, really important. Make sure that the parts that you're buying match the footprint. I cannot stress that enough. Also, this ground symbol here is horizontal, which is not great. It should be like this. And the ground label itself isn't really necessary. You don't really need to have that visible in the case of this project, since, as I said earlier, everything is tied to the same ground and you just don't need to show it. Once again, we have the datasheet link here, which is just not needed and unnecessary. Looking at the rest of the schematic here, we see that there is no title, no date, and no project name. So didn't necessarily do a great job with that, although I didn't know how to fill out the schematic page at the time, nor did I look into resources to figure it out. I did put some notes here, and I read these notes in my free time, and they're not needed. If I really, really, really needed these notes, I should have just put them as a separate Word document and not actually in the schematic. But again, I didn't really understand that at the time, as this was my first project. So that pretty much covers everything with the schematic. It's very rough around the edges, like very, very rough. But I think it's really good to look at to see like how far I've come, how much I've learned. I clearly know a lot more information regarding electronics and circuit design in general. And, you know, it's a good indicator to show where I've started. And like I said earlier, throughout this channel, I'm going to show you my progression to becoming a better electronic engineer. But with that being said, we'll now move on to the layout portion of the video. So looking at our layout portion here, we could see once again that I'm missing a title page, missing the date, and just missing general information regarding the project. I didn't know how to fill it out at the time, so that's why I didn't put it there. The PCB itself is rather small. It's only 53 by 31 millimeters. And if we pull up the 3D view here, we could see that I actually have most of the 3D models for the components, although I am missing a 3D model for the USB type A connector. And the reference designators for pin 1, I do have them here, but they're kind of strange. They look like a Cheerio. I think I didn't know how to actually fill out the shape that I was making, which is why it looks like that. The board itself also does seem to have vias for stitching purposes, which is good, although I didn't know why I exactly needed them at the time. I was kind of just placing them randomly. And I put my name on the board, but for the sake of this video, I just put my YouTube channel name here. And I think that was all the silk screen that I had on at the time. I didn't put what year I made this board, the name of it, rev number, nothing like that. Once again, this was my first PCB, so extremely rough around the edges. But let's get back into the actual CAD portion of this. So if we look here, the trace width is extremely large at 1 millimeter, which again, if the circuit actually worked given the actual current output, that is not needed. I probably could have got away with a 0.3 to 0.5 millimeter trace. Also, there seems to be little to no spacing between traces, and certain parts themselves. Like this trace is extremely close to this resistor. Same thing goes for the ground traces here, which I clearly did not understand the point of a ground plane. So when you have a ground plane here, because this board has two layers, the front copper is ground along with the back copper being ground. You don't need to run traces to every single ground point. Again, at the time, I only built circuits on breadboards, so everything needs to be tied back to that ground rail, point to point, basically. And that's what I was doing here on the PCB design, which is just not necessarily at all. Also, you could see here the different grounds that I had, which, again, for a circuit like this, you want to keep ground the same for all components, so it's just not needed. It seems like all my traces are at a much higher width than they need to be, and just the layout of parts in general is not great. I do remember following the recommended layout for the boost converter itself, although again, I could have moved these parts closer. I noticed how none of them have their reference designators, which I had them on the schematic, so if anything, I should put them on the layout. Now, this is a topic for debate, as some people don't put them on their boards at all. However, in the case of at least prototyping, I believe you should have your reference designators for, at the very least, your components and not your ICs. So none of them are present here, which would also make assembly for myself much harder. As we can see here, the battery pads too are extremely small. There's little to no room to actually solder on the connector here, and I don't even know if I was able to be successful with it at the time, given how small it was. Other than that, there's not really too much to talk about. I mean, this circuit just didn't do anything. It's as simple as that. The LED for the charging IC, I don't even think that turned on. Maybe it did. But other than that, this was just a glorified LED board. Because, like I said, the boost converter is completely wrong. The protection IC is completely wrong. There is no connector to actually charge the lithium-ion battery. And, you know, it just was just a really, really poor layout. And a clear misunderstanding of how a good PCB design should be. So that was basically my first project, and what I want to do now actually is show you a more recent project that I did with an MQ2 gas sensor. Now this project, while still very rough around the edges, shows a lot of improvements from this particular project. So let's dive into that. So real quick, we'll just go through the schematic and layout of this project, and as you can see just from the title page alone, this is a huge improvement. For starters, we actually have proper information detailing the purpose of the project, the date it was created, the revision number, along with who created the project. We have mounting holes, so if I want to put this board in an enclosure, I can. And we have a scope pad, so if for whatever reason I need to use an oscilloscope to probe different points of the circuit, I have an easy access to the ground of this circuit. Over here, we could also see that I have separate schematic sheets for each section. For more complex projects, this is good practice, although again for the portable phone charger it wasn't necessarily needed. However, it would have been nice to have a block diagram like I have here, as I feel it just gives a good visual representation of what's going on in the project. I won't get into detail how things are interconnected here, but if you want me to make a video on it, just let me know in the comments below. If we look at the power section here, we could see more of the same good principles apply. Reference designators are neat and organized. We have notes regarding properties of components. We have test points to measure with either a multimeter or oscilloscope, jumpers so that if we want to disconnect certain part of the circuits, we could just simply remove solder from there. And we have fuse for overcurrent protection and an ESD IC connected to the data plus and data minus lines over USB connector. If we look at the LiPo section of our project here, which involves a charger, protection IC, and boost converter, once again we have a much better layout and just view of the project overall. So ICs have the input pins on the left side and output pins on the right. There are also net labels for each particular pin, which is very useful when designing the PCB, as instead of having that generic net number, you'll have the custom label that pertains to the pin of the IC, which is also good if you're going to send this design to somebody, and they'll have a much easier time looking at it and understanding how things are connected and why they're there in particular. If we look at the protection IC here, once again, massive improvement. We could see that the lithium-ion battery actually has its own symbol, net labels, along with jumpers, and I have a fuse in line, which is good for overcurrent protection situations, and even a power rating for the FETs, and just important properties regarding the IC that I chose in order to protect this battery. Looking at the boost converter here, we could see I actually have resistors for the feedback pin, the formula regarding calculating the resistance, and just some important properties of the actual boost converter itself in regards to the current output and duty cycle. So that's pretty much it regarding the schematic. We'll now look at the actual layout of the board, and if we go to the 3D view, we could see once again massive improvement. There's just a more systematic approach to this that I feel was missing with my first project, and there's even labels for each section so you know what this particular IC is doing. So if I look at this IC here, I know it's the UART connection, this is the microcontroller, this is the LDO regulator, USB connector, and so on and so forth. Here we could also see test points, and trace widths are appropriate length and size, along with our jumpers that we can easily connect and disconnect the circuit for. And like I said previously, it's just a much better layout and configuration of the board. There's no ground traces that go from ground to ground to ground. I'm actually using the copper pour here properly instead of tying it like a breadboard. And just in general, it looks much more appealing to the eye. We have proper pin 1 designators, and components are in good placement and follow the recommended layouts from their datasheets, unlike the previous project for at least some of the ICs that I chose. So yeah, overall, just a massive improvement in so many different ways. And there's still a lot to learn. You know, I'm still growing and learning as an electronic engineer and still making mistakes, but I've learned a lot from the past, and I kind of just wanted to show you that this is where I'm at currently, and I'm hoping in the next year or two I could look at this board again and be like, wow, this really wasn't that great. Now look what I'm making. So that's pretty much going to be it for this video. I'm hoping to make a lot more in regards to embedded engineering, programming, custom PCBs, and just small little one-off circuits and breakout boards in general. So thank you all for watching, and have a great day.